So our last speaker of this morning session is Florian Metzler, a local speaker, if I understand well. I know, but please go ahead.
Yeah, I'm originally from Germany, but I'm based in the United States. And this is our group here, mostly at MIT, but also in the UK and in Switzerland. And the names that are green are the ones that are here. We actually have a lot of team members here at the conference. And the work that I will present is based on the ideas of Professor Peter Hagelstein that he developed over the course of his career, but that our team has refined over the last couple of years. And I want to situate this, so the title here is Nucleonics, towards the precise control of nuclear states. And I want to situate this a little bit. What do we mean by nucleonics? A few years ago, we had this paper, The Emergence of Quantum Energy Science, where we highlighted similarities that we noticed across quantum computing approaches to the rational engineering of organic solar cells, quantum batteries, and the kind of work that we've been doing looking at collective quantum effects at the nuclear level. And so this is what this talk will be focused on. And we introduced this term nucleonics as a counterpart to electronics. So Wikipedia defines electronics as a scientific and engineering discipline to create devices that manipulate electrons, and you could just swap electronics for nucleonics and electrons for nucleons. And what that means you will see in a minute. Okay, so I'll use nuclear batteries, or the notion of nuclear batteries, as an entry point to this. And I had some discussions with James Crouch yesterday, who's been thinking about this as well. And there is a whole literature on nuclear batteries, but that is really an incoherent literature. So, for instance, there is this isotope of molybdenum that has an excited state around 2.4 MeV that has a fairly long lifetime of around 7 hours. And people have excited that state with a synchrotron, and then you can wait for it to decay, or you can try to accelerate or induce the decay by going to a higher level that is more unstable, and then it falls back into ground state. So that's the notion of a nuclear battery that would need to be charged and then can be discharged. There is also a notion of a nuclear battery that is pre-charged by nature. And so if you go mine tantalum, 0.012% of the mined tantalum is actually in a highly metastable state with a lifetime, I think, of, it's given here, 10 to the 15 years. So that'll just basically act like a stable nucleus. And however, its decay can be induced, and the same kind of strategy, you bump it up to a higher state that's unstable, and then you fall back down to ground state, and the energy comes out. And so that's the typical triggering approach. You go from the metastable to a highly unstable state. And when we discuss this with James, he and his group have some ideas about using maybe superabsorption to improve that process. So we've thought about things along similar lines, but slightly differently. So we'd like to get energy out of metastable nuclear states by moving them, not by superabsorption, but by supertransfer to resonant receiver states, resonant receiver nuclei, which then have highly unstable states and decay to ground state, and get the energy out this way. And instead of tantalum 180M with about an 80 keV metastable state, we're looking at another system that has a highly metastable and also a high energy transition state that is a deuterium molecule. So if you consider a deuterium molecule from a nuclear perspective as a system of highly clustered nucleons, then you can model it as a two-level system that goes from the D2, the highly clustered 4-nucleon configuration, to the compact 4-nucleon configuration, which is what we recognize as helium-4. And so we've done this in our articles that I'll show in a second. You can look at the nuclear wave function for the deuterium molecule. So this is the nuclear wave function that determines what the probability density is of finding the nucleons in a certain place. And then you can look at the transition and how it's hindered, and get the probability density for finding this system in this compact configuration, this compact stable configuration of helium-4. And so you go from here to here. And there's a Nature paper by Kunin and Naunberg that have modeled this. It's kind of a benchmark, and it shows how extremely metastable a deuteron pair really is. So with an estimated half-life of 10 to the 56 years. So even more metastable than the tantalum. 180 M state. And so we created a bunch of different illustrations. So here you see that's this kind of spontaneous state transition that, with an extremely long half-life. And so eventually when the transition happens, the energy comes out in the form of either a photon or charged particles and neutrons. So those are the kind of the different decay pathways. And so this is the backdrop against what we're doing our work, and the main results have been published in this New Journal of Physics article, as well as there's an evolving document on arXiv, and then we have a very active GitHub page where there's lots of notes, documentation, codes that you can check out if you're interested in this. So the basic idea is we're looking at a deuteron pair that's in a metal hydride. So and metal hydrides are a well-known material system where certain metals like palladium or titanium absorb hydrogen or hydrogen isotopes readily. And the idea is then that you stimulate a coupling and then induce an excitation transfer from the D2 system to a resonant receiver state in one of the coupled nuclei. And that nucleus would then get excited and then disintegrate by particle emission. So the first issue is, okay, what could we use as a resonant receiver state? So the D2 to helium-4 transition has 23.848109 mega electron volts. And so it's unlikely to find like a single palladium state at exactly that level, or other metals for that purpose. But palladium is kind of a model system for metal hydrides, which is why we've looked at it as a concrete example in this modeling effort. So, but maybe at this early point, we can assume there's a hypothetical palladium excited state that matches this, and we can later in this presentation, I will update this assumption with a more realistic one. And then for nuclear states at that high energy level, most of them, the vast majority of them, will just disintegrate very quickly. And so that would satisfy the setup that we wanted for getting the energy out of a metastable state. And then we can set up a basic excitation transfer like a diagram scheme here with the two nuclei as two-level systems and that are coupled to a bosonic oscillator. And we'll look into what oscillators we can consider here also in just a second. But then the setup would be like this. So you wouldn't have the deuterium pair in isolation, but you would have it coupled to a heavy nucleus, and then that goes into an excited state. And here, what's illustrated here are Rabi oscillations going back and forth. And when the coupling breaks down and you happen to have the heavy nucleus excited, then you would get the fast decay of that heavy nucleus and the emission of the energy. So this is the general idea here. And in going about modeling this, I'd like to refer back to this 1965 physical review letter by Terhune and Baldwin that already pointed out that when you have nuclei embedded in a lattice and participating in collective dynamics, then you cannot model nuclei in isolation, but you have to treat them as part of a Hamiltonian. And they recommend this Hamiltonian here as a starting point. Our Hamiltonian looks very similar to that. And that's a very complex Hamiltonian, of course. So in our papers, we go through a reduction and we end up with a nuclear Dickey model, which in this case is still expressed in a very general way. So here there are different couplings, but this model is still agnostic to what coupling is considered. And again, we'll get to that in just a second. And from that model, we can get a rate expression for the transfer rate going from the state on the left to the state on the right. And that basically includes a loss factor, and then the two types, the couplings on the donor side and the receiver side over the transition energy, and then some Dickey factors. So first I want to now look into what are potential receiver states that are actually available rather than using our hypothetical resonant palladium state. So the first starting point here would be to go to the nuclear databases. And you can go to any element and you can identify the stable isotopes and pull out the nuclear excited states for those isotopes. But then there's already one headache, which is it's well known in nuclear physics that the higher you go in energy, the denser the states should become. And that's not what we see here with these states extracted from the database. There is one nucleus in that mass range, which is tin 120, that has been better characterized than any other isotope. And here we see that relation actually quite nicely. So you get a high density of states as you go higher. But what's the same with all of these nuclei is that they disintegrate between, this is represented here through the gray area. So somewhere between 8 and 10 MeV, they tend to disintegrate, for instance, through neutron emission, alpha emission. And so then you may ask, okay, how do we even get to 23.4 MeV, 23.84 MeV that we need to get to? Well, there's another kind of nuclear states. So the states from the database are bound states. So these are basically spherical nuclei that go into different states of excitation, for instance, quadrupole vibrations. But then you have more exotic nuclear states that are spatially clustered, and then each cluster has its own substate, and they have to be all considered together. So this is a whole literature on nuclear cluster, nuclear molecule states, and there are many different configurations. And those kind of states tend to be more stable and also tend to be higher in energy. So in our group, we did some basic liquid drop models of these states, and these are estimates we get for nuclear molecule states available for the stable palladium isotopes. And you see, you get much higher, you get a high density of states, especially north of 40 MeV. But then here too, we actually have the headache that in the region of interest, 23.84 MeV, there isn't a very high density of states. And the states there are sometimes a few hundred or a few thousand keV apart. And then just to illustrate also here for these nuclear molecule excited states, they actually tend to take a shape that is more symmetrical as you go to higher energy states. And eventually, when you're in like the beyond 40, 50 MeV range, then they tend to disintegrate through fission. And then, so here now superimposed the bound states, and so that's basically what we can work with. And so then we considered, because there's nothing there and nothing suitable there, 23.84 MeV, so we considered combinations of bound states as receiver states. And that would basically look like this. You have your deuteron pair, you activate the coupling, and then you're de-exciting the deuteron pair to helium-4, and you're exciting these multiple bound states. And so when we look at the bound states, for instance, from tin 120, and we consider all combinations of two different nuclei, it's pretty much the same for palladium as for tin 20, since nuclei in this mass range behave similarly. So we can expect a much higher number of states per 100 keV, and then we consider up to three states, then we get a pretty high density of states. So these are up to 3 palladium nuclei acting as combination receiver states. So then we are already at a point where we have hundreds of states per electron volt. And so the level scheme would then move from this 1-to-1 transfer to 1-to-2 transfer, and 1-to-3 transfer, or 1-to-many transfer. And so the rate expression changes in the sense that on the receiver side, you get the coupling on the receiver side come in multiple times, and they multiply onto each other. So then the strength of coupling plays a big role, because if your coupling is weak, then you're just amplifying that even more. And then we had another version of the model that I don't have time to go into, that not just considers a single state on the receiver side, but the full density of states, which is very high on the receiver sides, and also a phonon exchange or energy exchange with the oscillator mode. Okay, so then we found a way to achieve resonance if we have strong enough coupling. But let's talk a bit about coupling and decay enhancement. So nuclei are very small, so the dipole-dipole couplings tend to also be very small, and they decline very quickly with distance. So what we need to begin with is an externally driven coupling where nuclei are coupled to a shared oscillator with a large spatial extent. And we considered magnetic dipole coupling, electric dipole coupling, and then a more exotic type of nuclear coupling called relativistic phononuclear coupling that has been explored by Peter Hagelstein, and that results from Lorentz contraction during the acceleration, deceleration of oscillating nuclei. And so we can estimate some upper bounds for these different types of couplings. And so for the magnetic coupling, an upper bound, there's constants like the nuclear magneton, and then there's upper bound in terms of how strong your magnetic field could be. And similarly, there's constants here, like the nuclear radius for electric coupling, and also there's practical limits to the electric field you can apply. And there's also constraints for this relativistic phonon nuclear coupling, which is the kinetic energy that can go into phonon modes before the lattice disintegrates. Nevertheless, we can see if we can compare those couplings, the relativistic phonon coupling, while still weak, is stronger than the other ones. And so this is the coupling that we work with. And then if we bring in the transition energy and look at the normalized coupling, where the coupling is divided through the transition energy that then enters into the transfer rate expression, and we see that the numbers are still very small. And if we want to transfer to combination states, then this will still be very small rates. So we need Dicke enhancement factors. But then, for instance, if you take a 5 megahertz oscillator, the coherence domain is very large, and you have a large number of nuclei involved. So we expect some very large Dicke enhancement here. And if we consider this 5 megahertz oscillator with a 200 micron cubed area, then we're getting actually Dicke enhancement factors on the order of 10 to the 9. And so then we are actually in the strong coupling regime for the relativistic nuclear phonon coupling. And so that would mean the transfer to these combination states would actually work. And so if we go back here to the rate expression that I showed earlier, we can then plug in, we can develop and get these terms into to include the experimentally accessible parameters. And here is what we plugged in, and we end up with transfer rates on the order of 1 per second. And that may sound fast given how stable nuclei are, but it's actually still a problem given how we wouldn't expect the coherence that we need here to last that long. And also the receiver states, these bound states, have very short lifetimes, which we have documented in the paper. So we have been aiming for something on the order of a nanosecond. And this is indeed what we get when we consider the more complicated version of the model that considers the full density of states as receiver states, and also that takes into account these kind of the phonon exchange between the nuclear states and the lattice. So this is, and then we can develop some scaling relationships from this, where the transfer rate can be expressed as a function of the energy that's in the phonon mode, of course, only to a limit until the phonon mode disintegrates, the lattice melts. So this would be the kind of operating mode that this process would like to be operated in. Okay, so this is just an introduction to this work that we've been doing. I wanted to take a step back and share a little bit about the motivation and strategy in the last minute here. So we're, on the one hand, interested in developing simpler first principles demonstrations of this Dicke-enhanced nuclear excitation transfer or nuclear supertransfer type of effect. But then we're also motivated by reports of anomalous nuclear particle emission from metal hydrogen systems like palladium deuteride and titanium deuteride. And so we have this kind of bottom-up and top-down motivation here. And so if you want to learn more about those two aspects, we have two posters one on each of these. And on the basic nuclear excitation transfer experiments, we've been considering a version of iron-57 is a kind of a workhorse for nuclear physics and engineering because it has a very low-lying 14 keV state. And so one of the experiments we envision is to induce excitation transfer between iron-57 nuclei. This relativistic coupling would be, again, the strongest, but because it's more exotic, we've also considered versions of this kind of excitation transfer with the magnetic coupling, but then we would need to transfer to electronic states in order to avoid the weak coupling coming in twice in the transfer expression. And then we've also considered using this low-lying thorium state that's only around 8 eV, that's a truly exotic nuclear state, as a potential for demonstrating nuclear supertransfer. So if you have interest in this kind of work, then please approach us and maybe we can collaborate. In terms of the empirical motivation, so we have an experimental effort as well, and that is under the U.S. Department of Energy, where folks were interested in looking into these reports of nuclear particle emission from these kinds of systems. So it's often very simple setups where you have a metal that can absorb hydrogen or its isotopes, and with some sort of stimulation then results in particle emission. So a typical setup would be, for instance, a palladium thin film that's infused with deuterium. And here is a paper that's the first in that table that reported bursts of neutrons from this system or from a similar system, and there was a neutron detector in the background that did not see such bursts. There's very careful work done at the University of Illinois that reported charged particle emissions through track detectors where you can determine the angular incidence. And then there is reports of surface modifications where the spots that formed after this kind of hydrogenation of the sample suggest the formation of lower Z elements. And these we compared those with the known palladium fission daughter products of palladium isotopes, and they were all there. And so I'd interpret this as the induced fission of palladium nuclei. So it would be a DD to helium-4 transition that it would induce, or multiple DD to helium-4 transitions that would bump you up into this higher 40 to 50 MeV energy range to induce the fission of palladium. And so that's basically our interpretation and our motivation for this kind of model development to see whether there could be explanations for these reported anomalies. And this is just a summary slide of our experimental effort. So we're in the process of replicating some of these experiments and then converging the experimental observations with the modeling work. Thank you very much.